Greetings. In this video, we will take care of a particular problem in multivariable calculus, and it will be a double integral. And what it means is we have some 3D axis, x, y, z, and then there's some curve in 3D, which is made up in the way that it goes with input from x and y, and it goes up in the z direction, all these points, and they together make a surface on that. And now I want to see what is the volume of like below this curve that is spread out in the 3D space. So we have, for example, this some surface, and we want the area of that between 1 and 2 in the y direction, and we also want to take it 1 to 2 in the other direction, in the x direction. So that's the idea here. And now I have to specify what kind of surface this is going to be. So I mean, I can think of anything, and what we really want to take care of in this video is the actual mathematical calculation of this. So what I'll do is I'll say that this surface below which we're looking for the volume, and by the way, the volume goes from the height of the xy plane, it doesn't go below, so it's between the xy plane, the volume between the xy plane and this bounded area, that's 1, 2, this square, and so about this bounded by this square going up until the surface, which will have some more complex shape because it won't be just a linear function. I'll actually choose something more interesting in that aspect. So I can say f of xy, so because this is a surface going from the xy plane and it has all the, so the inputs are from xy and the outputs are in the z, all these points that make up this surface, is going to be a function of x and y, and it's going to be integers of x and y. And it's going to be the z. So z equals f of x and y, I can also write it here, by the way, equals f of x and y, and now I'll make up a function. So that can be, for example, 1/2 of x squared y cubed. Right. So this is my function, and I want to know what is the volume between the xy plane and until we get to the surface if I'm bounding the calculation by 1 to 2 in the y direction, 1 to 2 in the x direction. So it's going to be a double integral, and there's two sigma signs as we see, dx, dy, by the way, the differentials there. So yes, these two integrals stand for the two independent variables we have. So we calculate these integrals, I'm going to show you how, and then we get the volume bounded by this 1, 2 square below, and by the surface 1/2 x squared y cubed from above. So how this is taken care of is inside this integral, I'm going to put exactly this function. So that's 1/2 x cubed x squared y cubed, and this is a scalar. I take out the 1/2 outside the whole thing, and now I'm going to calculate. And here actually it doesn't matter which we do first, but there's a particular thing we have to keep in mind. How does this work? Well, this sigma, this inner sigma, is connected with this inner dx, and then we take care of this first. And then this outer sigma, or I can even do it with the 1/2, doesn't matter, is connected with this outer dy. So that's what I do here. And what I have to keep in mind is, when I'm doing the inner one, it's in respect to dx, and I'll treat the y's as constant. That's the point of double integrals, or triple integrals, multiple integrals in general. You treat other variables as constant, and you only take care of the one that it's in respect to at that point. Alright, so I'm going to do that. But also, not to forget, we have a bounded area from below. It's 1 to 2 and 1 to 2 in both x and y. So I'm going to bound the integrals respectively. Both cases are the same bound, so I can just reproduce the same thing, 1 to 2, 1 to 2 in both cases. So now I do the dx one. Right, so I rewrite the whole outer dy thing, and I care about the inner dx thing. Right, so what is that? Well, I take the integral of this function in respect to x, that's x cubed over 3. And then I multiply it by the y thing, which does not change at all. Right? And then I have to evaluate it at the bounds of x, which by the way happen to be the same like the bounds of y, but it doesn't matter. That's 2 and 1 from below and above. Alright. So I evaluate this first, and then I'll take care of the outer dy. So now I just rewrite the outer dy thing. I'm just taking care of this inner parentheses part all the time. Alright. So what do I get is 8 over 3 y cubed minus 1 over 3 y cubed. So that's the inner parentheses dy. We've taken care of the dx part by now. Alright, and now that we get that, well, I can simplify this thing. It's going to become 1/2 and then it's gonna be 7/3 y cubed. I take the 7/3 completely outside. And then we have integral of y cubed dy. And yeah, by the way, we have to keep the bounds, not to forget about those. So I could have been writing them all along here, and I do them here. And now, only thing I have done after all this, the x has been taken care of and evaluated. That's why we only have numbers and the y left. So now evaluate to y. So I multiply this, 7/6, alright? And then we have times this integral. That's done the completely normal way. Alright? Like simple integrals with simple number evaluations. And that is 7/6 times, and now we evaluate this, which is 16/4 minus 1/4. So the whole result of this is 7/6 times 15/4. And I mean, we can work this further. We can divide this and this by 3. So it will be 7/2 times 5/4. And that is 35/8. So basically that's interesting. So if we have this function, 1/2 x squared y cubed, and we want to find the volume between 1, 2, 1, 2 square on the xy plane going till the surface, whatever the shape actually is, and then in reality, then that area will be exactly 35/8. Alright, so just to revise the whole thing once again. So to get this area here, this volume down up here, we use double integration, and double integration works in the way that in this particular case, it didn't matter which we did first. If we take care of the dx inside and the dy outside, both for the reason that, like already we see here, by the way, that's another interesting thing to see, the bounds for both the integrals is 1 to 2. I made it that way. We just chose this particular base area from below. And then, shape of that. And then we have a double integral. Each of them stands for one of the independent variables. And first, we take care of the inner one. We solve it as if the other variable is a constant, or a variable that's not taken into account as for the integral. So we have this inner dx one. We integrate in respect to dx. We take care of the x antiderivative, but the y cube stays there as a constant, completely unchanged. Then we evaluate 2 and 1 for the x. Then we get something only in respect to y and numbers. The numbers got out a lot, and then we got only a y integral, again with the bounds that we have to follow all along here, and then we got all the way here to a number.